So now we are studying about the spectrograph theory. We are seeing some examples of the relationship between spectrum of the graph and some graph property. So now we want to talk about independent set and chromatic number. First, we talk about the independent. So again, the graph has the spectrum. Either it's eigenvalues of the adjacency matrix or the Laplacian matrix. They contain some information about the graph regarding the independence number, the biggest size of the independent set in the graph. One of the well-known theorem is Hopman's bound. It's regarding the independence set in regular graph. So let's be a D-regular graph. And the independence number is related to the smallest eigenvalue. Let mu sub n be the smallest eigenvalue of the graph, the adjacency matrix of the graph. Then the Hopman bound says that we know that this mu n is a negative number. Then we get this. So, but this is only for regular. So we have this assumption that this is for the regular graph. Then what if we consider general graph? Again, the Laplacian is invented to deal with non-regular graph. There are certain techniques that you can use to derive some facts from the regular graph, and then you want to generalize this to non-regular graph, then you use Laplacian. So, the following theorem implies this Hopman bound and then also deal with the non-regular graph. So this is by Goshil and Newman in 2008. So let S be an independent set. In G, and let's write this sub average of S be the average degree of a vertex in S. Just for each vertex, you add the degree and then you divide by the size of it. Then, for any independent set, we have this inequality where this lambda n is the largest eigenvalue of the Laplacian of C. Okay, first let's check that this actually implies Hopman bound. So if G is the irregular graph, what does this say? This is what? The average degree in the vertices in S is D, every vertex has degree D. And this lambda n, what we know is that for regular graph, this lambda n is nothing but d minus mu n. So this is d minus mu n. Then what does this become? This is d minus mu n over d minus mu n minus d times n. So you just cancel them out, then you get this expression. So every independent set satisfies this, and we get this Hopman bound. So this is indeed stronger than Hopman bound. And the proof of this is easy. So again, this is the largest eigenvalue of Laplacian. That means that no matter what vector you take, its Rayleigh quotient is almost lambda. So by Kurai-Fisher, we have that this lambda n is for maximum over all vector, you take the Rayleigh quotient of the Laplacian. And so if we take a specific vector, then its Rayleigh quotient is most lambda n. And we want to take this specific vector as a vector that's related to this f. In particular, one good candidate is the characteristic vector for this f. But if you do the computation, it's actually better to take the following vector. So you take the characteristic vector on this f, and then you subtract this. So in other words, what does this become? This is that this is vector, the column vector, say that this part is corresponding to s, this part is corresponding to the remaining. Then here you have 1 minus 1 over s over n, all the coordinates are in this way. And then here you have all the coordinates are this. So in other words, it's a vector which are have two different values on s and then outside of s. And then you choose this number in this way so that the inequality you get at the end is, getting as strong as possible that we get. So then what do we have? We can now try to compute the Rayleigh quotient of this vector. So if we take the numerator first, what does this become? So we know that this Laplacian satisfy that the L of times the all one vector, constant vector is 0. So here, you might as well just evaluate with this. So these two are things. So this part is added to, minimize to, optimize the inequality that you get. Yeah. So for computing this upper part, this does not really contribute. Then what's this? So as we mentioned before, if you have this expression, this quadratic form, this is nothing but you take the xi coordinate minus xj coordinate, and then take the square for all ij in the edges. So in the same way, here, again, for all h, you take the i's coordinate of this vector minus j's coordinate of this vector, and then you take the square. But what do we know? So this term disappears if both of them are 1 or both of them are 0. They survive only if one is in F and one is outside in F. So this H is sticking out from S to outside, then this survives. And S is an independent set, and then this is exactly counting the number of edges. Number of edges from S to outside. And that's what? Let's write it this way. Let's summation of the all degrees of the vertices in S. Let's write it as D of S, which is the D average of S times S. Okay, maybe we don't have to even define this notation. You just write it this way. So now we have this denominator, enumerator. So we now compute the denominator. So what's this? So as I mentioned, this is what vector whose coordinate corresponding to S, and outside of S is 1 minus S over N, or the coordinate here, and then here it's minus S over N. So let's write small s as the size of S divided by N. You write it as the small s. And this is size of S, it's many coordinates, so 1 minus S squared. So this is 1 minus S plus N minus S, remaining many S squared. So you just compute this, then what? And well, let me write it in a way that this is capital, this is small cap. Then you can compute that this is like N times S minus S squared. Now we are at the end. So this Rayleigh quotient is at most lambda N, and this is what the average of F, average degree of S times S, as we computed here. And on the bottom you have N times S minus S squared, which is NS times 1 minus S. So NS is S and 1 minus S. From here, what do you get? You get that 1 minus T average of S over lambda N is at least S. And this is the size of S divided by N. So size of S is at most N minus N times 1 minus the average of S divided by lambda. So we get the inequality as this side. Okay. So this roughly give you the upper bound on the invariance number of G if we know some distribution on the degrees of the graph. Okay, from this, if we know upper bound on the alpha, then the chromatic number is at least N over alpha. So you get some lower bound on G. On the chromatic number. But can we get more explicit one? So here, if the graph is irregular, then you get the upper bound and then you get this. But otherwise, you have this term, which is difficult to control. So it doesn't really give you an explicit bound on the chromatic number that you want. So natural question is that can we find some bound on chromatic number using this eigenvalue? We already have shown this upper bound. In terms of the largest eigenvalue of the ordinary symmetry. And can you find the lower bound? That's an example. I mean, that's a natural question. In terms of lower bound, in terms of eigenvalue. So, as I mentioned, this plus the Hochland bound for the regular graph, this yields what we want. What if we have for non-regular? So there is this theorem which said that this chromatic number is at least 1 plus mu1 divided by negative mun. So again, this mun is negative number, so minus mun is positive. So this is actually positive number. So we have this theorem, which is what we want, which is a lower bound in terms of this eigenvalue. So this is actually a generalization of the theorem that before we show that the bipartite graphing bipartite implies that mu1 is same as negative mun. We have seen it. And in fact, the other direction also holds. I mentioned it without proving it, but it's also not difficult to prove it. Anyway, so we have this. And this statement is in some way a generalization of this statement. So if we have this, then what do we know? If this is 2, and this is at most 2, so this is at most 1. But we know that this holds. It's also not difficult to prove. It was one of the statements inside of the Perron-Provenance theorem that we didn't prove. But as we know this, the fact that this is 2 implies that this upper part and lower part have to be same. So this is a generalization of this statement. So multiplicative gap between these two values cannot be too high unless your graph has high chromatic number. So let's prove this. So first we want to prove the following lemma. In order to state this lemma, let's say for a given matrix M, this is, let's write the lambda mean to be the smallest eigenvalue of L, and let lambda max of M to be the largest eigenvalue of M. So what we want to do is we want to utilize the fact that if you have a chromatic number, if your graph is K-partite, and you can reorder the vertices so that these rows and columns are partitioned in such a way that these parts are all 0, and these are symmetric, and so on. So if your graph is 4 chromatic, then you can do this. So we want to analyze this kind of matrix and then see how the largest eigenvalue and smallest eigenvalue of the entire matrix is related to each of these. So for that, we prove this lemma. So that M is the matrix so that we have M11, M12, M13, M1K. Here, you have, this is symmetric. And AK, you have M1K transpose, and sorry, this is with, yeah, M2K transpose and so on. So let's say this is a matrix which is a block partition. And K then is 2. Then what we can show is that K minus 1 times the smallest eigenvalue of M plus the biggest eigenvalue of M is sum with at most the summation of the biggest eigenvalue of this block diagonal block. Okay, so we want to prove this. And for that, we want to prove it in inductive way. So let's consider the most easy case of K equal 2. So let A be, say, B, C transpose D be a symmetric matrix. And we claim that this is true. So you take the K equal 2 here, then what? You have this. Let's prove this claim first. Yeah. So again, we want to use Rayleigh quotient to prove this. And so these eigenvalues using Courant-Fisher theorem, they correspond to the Rayleigh quotient of certain eigenvector. So let X be a unit eigenvector of A of the largest eigenvector value. And this X can be written as say W and G. And this part corresponds to B, and this part corresponds to D. So the length of this is exactly this size. Okay, then what do we know? The lambda max of A is Rayleigh quotient of this. Okay. Now we want to, so this is equality. So this can, we can just replace with this. Now we want to replace this with other Rayleigh quotient, but this is lambda minimum. That means no matter what vector you take, it's Rayleigh quotient. So no matter what y you take, its Rayleigh quotient is bigger than or equal to this, right? So by upper bounding, it's not a problem. So we can get anything, but we want to take these things so that we can finally get these two terms at the end. For that purpose, we use this. So based on this, we define y in this way. So this definition is based on trial and error. Later you do this computation and then try to see how you get this, and then that motivates the solution, this choice. And roughly this is also analogous to the previous choice. In bit 4, we were dealing with the bipartite case. What we did was we take this column vector, and then what you did is you swap it and then you multiply negative on one part. And then this is a bit analogous to this. So basically, you have, give me a moment. No, you didn't swap it here. Give me a moment. Let me check. Okay, so you denormalize this and then you take a negative on one side. Then what do we get? As I mentioned, we have that this Rayleigh quotient, because we take that as a unit vector. This is unit vector, so we don't have to divide it by x transpose x. We can just forget the denominator. And then this choice is again, so that this is a unit vector. That's how we normalize this. So this Rayleigh vector upper bounds this term. And you can actually compute this, because A is D, C transpose D, what? And then X is W, and then G. So this is W transpose D, W, plus W transpose C, C, and then G transpose C, transpose W, plus G transpose D, G. So that comes from here. And then there are additional 4 terms coming from here. And you can compute this. You get this. And here, this term cancels out. And these are the same term, these are the same term. So what you get is 1 plus the norm of G divided by norm of W times the W transpose B W and G transpose D G. So these are the Rayleigh quotient of B and D. But again, by Courant-Fisher theorem, they are upper bounded by the largest eigenvalue of largest eigenvalue of B and D. But here, what? You can actually write it as here W and G are not unit vector. You have to write this as this. So this denominator is actually same as norm of G and norm of W. And then you move it inside here, you move it inside here, then what you get? Norm of W plus norm of G times this is at most the biggest eigenvalue of B and the biggest eigenvalue of D. give me a moment. Sorry, so this is squared, and then, yes, I see. So this has to be squared. I have written it wrong. Because here you multiply twice here and here. So this is quadratic form, so these are the square. So you have this. And we know that the what? This is same as the norm square of x, which is 1. So you get this. So this proves the claim as we wanted. Then now what? We can apply this claim to prove this lemma. Again, we use induction. Proof of lemma is induction on K. Assume, say, B is the part that you have M11 to M K minus 1, K minus 1. And there are remaining parts. So you delete the last row and last column, then you get B. Then, what do you get? Then, by the claim, the entire matrix M is what? Lambda mean of M plus lambda max of M is M most the lambda mean of this C plus lambda max of this last term, MKK. And by induction hypothesis, what do you know? By induction, you have that this lambda mean of P plus lambda max of P, and you multiply K minus 2 on here. It's at most the summation of lambda max of MII from I1 to K minus 1. This is what we know from induction hypothesis. Okay, then level 1. There. So here I wrote it wrong. This is max. So what? Using an induction hypothesis, this one is, you can move this one to other side and then subtract it. Then what you get? So you get this, and then this is M most minus K minus 2 lambda mean A plus summation of I equal 1 to K minus 1 lambda max MII. And then you add this, so you just write this as K. You'll be happy. But what do you know? By Cauchy integration theorem, this lambda mean is this is at least lambda mean of A. So you can replace it with the lambda mean of A plus this summation. Now what? You just move this to the other side, then you obtain what you wanted. No, not A, this is M. So this proves the lemma. So now what? Using this lemma, we can prove the lower bound on the chromatic number in terms of its eigenvalue. So what? If chromatic number of G is K, then the address matrix can be written as 0, 0, 0, 0, and say 1, M1, 2, 2, M1, K, and then M1, 2 transpose to M1, K transpose in this way. So this diagonal blocks are all 0. And by the lemma, what do we have? K minus 1 times mu n plus mu 1 is at most the summation of lambda vex of this mii, which are all 0. So this is 0. So we have what? And we know that this is negative and this is not negative. You can see from here the u1 is at least k minus 1 times negative mu n. So k minus 1 is at least negative mu n over mu1. No, mu1 over mu negative mu n. So k is at least 1 plus mu1 over negative mu n. So that proves what we wanted. Okay, and yeah, that proved what we wanted to prove. Okay, in the next video, we will do one more thing before concluding the section of the spectral graph theory. And next section will be about the counting number of spanning trees in a given graph. And the number of such a spanning tree is also related to the eigenvalue. And we will see that in the next video.